We're on section 5.2 on the definite integral. In the last lecture, we covered most of this section. We defined the definite integral and learned a little bit of how to work with that definition. And then we started looking at some properties of the integral. And we just have a few more properties to go to finish this section. So that's what we're going to start with today. Here we're going to present three properties that compare sizes of various integrals. And there's one point we need to make with these. The properties we've covered before now in yesterday's lecture, when we looked at our limits of integration from a to b, it didn't matter if a was less than b, equal to b, or greater than b. The properties were still true in any of those cases. But in these properties, these properties are only true if the bottom number a is less than or equal to the top number b. So we've made that assumption in all three properties. So property 6 says that if f of x is 0 or bigger for all x in a given interval, then the integral of f over that same interval would also be 0 or bigger. So this is easy to understand graphically. I'm going to make a sketch here. Here's my x interval. And then we've got a graph of some function that's always positive. So notice the function I sketch is all positive y values, no negative values. So if we sketch the region down to the x-axis below that curve, would be this region here. Notice because it's above the x-axis, in terms of areas, the integral counts that area as positive. And there are no negative regions to be counted as negative towards the integral. So under the assumption that f is 0 or bigger, it must be the case that the integral of f is also 0 or bigger. Okay, let's look at that's property 6. So property 7, we have two functions, f and g, and we've assumed f is greater than or equal to g. Okay, so we've got some function f, and then we've got some other function g that's less than f. Again, we cut it off at the sides here, a and b. So now look at the area below f is clearly going to be larger than the area below g. And that's what this statement is saying here, because this integral represents the area below f, and we know that's greater than or equal to the area below g. Okay, so that's our argument for property 7. For property 8, we've got this graph. So the assumption here is we have a function f of x that's bounded between two numbers. It's always greater than or equal to some number m, lowercase m, and it's always less than or equal to some number capital M. So here's our f. Notice its smallest value is here, so we'll call that little m. And its biggest value here, we'll call that capital M. So f of x is always between little m and capital M over this x interval from a to b. So under that assumption, this is the claim, that the integral of f is between these two expressions. Now let's look at those two expressions. So over here, we have a product of two things, little m and b minus a. Well, graphically, little m is this height, and b minus a is the length of that interval here. So the product would be the area of this rectangle. So I'm just going to write in here, the area here is little m times b minus a. Now look at this first inequality. This expression here means the area below f, which would be the area below this curve all the way down to the x-axis. That area is clearly bigger than the area of this blue shaded rectangle, which is what this first inequality says. Now let's look at this expression on the right. Product of two things. Capital M is this height. B minus A, the length of the x interval. So the product of those things is the area of this huge rectangle here all the way down to the x-axis. And so this inequality is saying that the integral of f, which is the area below the curve f, is less than or equal to the area of this big rectangle. And it's very clear from the picture that the area under the curve would be less than the area of this big rectangle. So this property 8 gives us a way to find a bound on the integral of f. If you're not able to find the exact value of the integral of f, you could use this property to find a lower and an upper bound for that integral. We're asked to use property 8 that I copied over on the right to estimate the integral shown here. So the function that we're integrating, right, that's called the integrand, is the square root of x. Now to use property 8, we need to get a lower bound and an upper bound for this function, square root of x. So let's recall what the graph looks like of this function. Right, this is the basic shape of y equals the square root of x. Notice the limits of integration go from 1 to 4, so let's mark those off. Okay, so we're just looking over that part of it. So we want to find the lowest point and the highest point of the graph just over this piece here. So because the graph is always increasing, right, the lowest part is here at the left endpoint and the highest y value is at the right endpoint. So let's find what those values are. So the lowest point, which is here at the x value 1, to find the y coordinate, you just plug 1 into the function. So the square root of 1 is 1. And then the highest point is over here at the right endpoint where x is 4. To find the y coordinate of this point here, just plug 4 into the function. You get the square root of 4, which is 2. So based on that graph, we can say that the square root of x is between 1 and 2 if we restrict it to x being in that interval, which is 1 to 4. So this is the little m and the capital M, right? We found those here to be 1 and 2. Okay, so now we have everything we need for the setup. Now we can arrive at our conclusion. So we're going to have our integral will be in the middle. And then we'll have inequality signs less thans on both sides. Now on the left side, we take little m, which in our case is 1, multiplied by b minus a, right? And that a and b were given here. A is 1, b is 4. So b minus a will be 4 minus 1. And then on the right side, we have capital M, which we found to be 2. And that's also multiplied by b minus a, so 4 minus 1. So then we'll simplify. We'll keep the middle part the same. And on the left, that simplifies to 3. And on the right, it's 2 times 3, which is 6. So we have a very rough estimate, right? Whatever this value is for this definite integral, we don't know what it is, but we can say it's between 3 and 6 using property 8. So right now, we probably couldn't find this integral. We don't have enough techniques yet. But you'll be learning more about that a little bit in this class and a lot more in calculus 2. You'll be able to find the exact value of this integral very easily after you learn a few more techniques. The midpoint rule was also mentioned in this section, so I just wanted to talk about it before we finish the section. We've actually already used it in some previous exercises we did. I just didn't call it the midpoint rule. So if you recall some of the past work we've been doing, we used Riemann sums, which are the sums of the areas of your approximating rectangles. We use those to estimate an area below a curve, which is the same as estimating the value of a definite integral. And we talked about how they use sample points and how the sample points can be chosen differently by different times. There's no rule to how you have to choose your sample points as long as they stay within each subinterval. We did some estimates where we chose the right endpoint as our sample points, and we did others where we chose the left endpoint as our sample points. And we did at least one example where we chose the midpoint of each subinterval to be the sample point. So here, the midpoint rule, all it means is you're doing that same type of problem where you're using a fixed number of rectangles to estimate the area below a curve. But with the midpoint rule, you choose midpoints as your sample points. Okay, so I'm not going to go through another example because we've done several of these already. And we did at least one where we chose midpoints for the sample points. And so here it's just restating the whole, this is what a Riemann sum looks like. The sample points here are called xi bar, right? Sometimes we call them xi star. And here, the reason they call it xi bar is that's the notation for the average, right? The midpoint between the left and right points of your interval can be found by averaging them, so add them together and divide by 2. Continuing in our chapter on integrals, Section 5.3 is on the fundamental theorem of calculus. So many branches of mathematics have a fundamental theorem. Right? There's one for algebra, etc. So here we're going to learn this fundamental theorem for calculus. Now this theorem has a very interesting result. It takes the two branches of calculus that we've been looking at. Right, we spent quite a long time on differential calculus and then just recently got introduced to integral calculus. And they seem like unrelated topics. The motivating problem for differential calculus is how to find the slope of a tangent line, whereas the motivating problem for integral calculus is how to find the area below a curve. Right? They seem completely unrelated. This theorem shows how they're actually very closely related, and we can actually view the derivative and integral as being inverse processes of each other. And that's what we'll be looking at in this section. The fundamental theorem of calculus has two parts. So we call them part 1 and part 2. So we're going to start with part 1. And this part deals with the function g of x defined in this way. So we have our integral sign. Limits of integration go from a to x, not b on the top, but we call the top the variable x. And then inside, our integrand, the function we're integrating, is f of t. And then because t is the independent variable, we use dt instead of dx. So what is kind of new here is that the right endpoint is now a variable x instead of a constant b. So let's think about graphically what this is representing. So I'm going to make our t-axis, the horizontal axis will be a t-axis, and then I'm going to create an interval that starts at a and it ends at some unknown value x that could change. So let's say a is here, and before I sketch x, let's sketch our graph. This is our f of t. Now the fact that the right endpoint is variable means we can choose it to be anything we want. So if I chose x to be here, then the integral shown there would be this area below the curve over that interval I sketched right here. But I could choose x to be farther to the right, and my area would now be all the way over to this new x. It would be a larger area in this case. And I could also choose x over to the left and have areas that way. And we discussed a property for how to deal with x being to the left of A. But the main point is the right endpoint is variable, and when we move the right endpoint to different locations, that changes the area, which means it changes the value of this definite integral. So now we view this integral as being a function of x because its value will be different for different choices of x. And so because of that, we can give the function a name, g, and say it's a function of x. Okay, now let's read a little more here. We are assuming that f is continuous because, as we've seen before, continuous functions are guaranteed to be integrable over a fixed interval. Let's see, then we have for each choice of x, whenever you fix x in a particular location, then this integral takes on a number, right? And that would be whatever the area is based on the region that's determined by where you chose x. So that's the kind of function we're going to be dealing with in part 1. We still have to get to the theorem, but this will be the function we're working with. In this example, we're given the graph of a function f, so we don't know its formula, but we just have the graph. And then we've defined this function g of x in a similar way that we just discussed. The integral from 0 to x, so the right endpoint is the variable x. And then we're integrating this function f that we have in the graph here. So based on this given graph, we want to find the values of g at various inputs, and then use the results to sketch a graph of g. So let's start with g of 0. So g of 0, if you look at the formula for g of x up at the top right, you can see it's the integral from 0 to x, but we've replaced x with 0, right? G of 0 means we're substituting in 0 for x. And then there are no more x's, so just copy the rest, f of t dt. Well, we had a property earlier that said if your limits of integration are the same number, the result will always be 0. And the reason is, right, if we're going from 0 to 0, we're finding the area below the curve over an interval that has no width. There's no region there to have any area, right? So the area has to be 0. Okay, next we're asked to find g of 1. So based on our formula for g, this would be the integral from 0 to 1 of f of t dt. Now in our figure, this is the region we're looking at, right? Because we're just going from 0 to 1, finding the area below the curve. And because that's a triangle, we can easily calculate that area. So 1/2 base times height. And if you look at the figure, the base right here is 1, length 1, and the height goes from 0 to 2, right? So that height is 2 units. And so simplifying this, we get 1. Let's go to g of 2. Definition of g says that's the integral from 0 to 2 of f of t dt. So I'm going to fill in the area of this triangle we just found is 1. Now we're going from 0 to 2. So now we're cutting it off here. So the area we're finding from 0 to 2 is this entire region here, stopping at the right when we get to 2. So breaking it into these two pieces, we could view this as a triangle plus a rectangle. And we've already found the area of that triangle, so now we need to find the area of this rectangle. So it is 1 unit for the base and 2 units for the height. So the area of that rectangle is, right, it's 1 times 2, which is 2. Okay, so back to our integral. The integral from 0 to 2, which is this entire area here, will be the sum of those two areas, so 1 plus 2. Okay, so we get 3, g of 2 equals 3. Let's go to g of 3. So that means we have the integral from 0 to 3 of f of t dt. So now in our graph we're going over to 3. So here's 3. And now we want to find the area of this whole region. So we can add together these 3 areas. We've already found the first 2. Now this one we're not going to be able to find exactly because notice it's curved here. We'll just try to estimate that as best we can. Notice if this were a straight line, it would be a triangle just like this one, same size as this one, which would be an area of 1. But by having this curved side, it's a little bit bigger. So we'll just guess it's about 1.3. Okay. So now the area of that entire region we see there will be 1 plus 2 plus 1.3. So that comes to 4.3. Now we're moving to g of 4. So integral from 0 to 4 of f of t dt. Now when we extend over to 4, the function becomes negative. Okay. So now we're going to need to find the area of this piece. Now notice how this piece here looks to be the same size as this one. So if we guessed this one to be 1.3, this one would also be 1.3. But because it's below the axis, we're going to count it as negative in our calculations. So now for the integral from 0 to 4, we've got part of it that's above the x-axis and part that's below. So when we add these up, the first 3 regions count as positive, and then we'll subtract 1.3 when we get to this last region. So altogether we've got 1 plus 2 plus 1.3, and then minus 1.3, and that comes out to a 3. Now we've got one more. G of 5 will be the integral from 0 to 5. So looking at our picture, we're now all the way over to here. So we've got another region to find the area of. Again, this looks kind of symmetric to these other two, right? So if these two are 1.3, this one looks like it's also an area of 1.3. But because it's below the axis, we'll count it as negative. So putting it all together for this final integral, we add the first 3 areas and then subtract 1.3 and then subtract another 1.3. And that comes to 1.7. So now we've answered the first part. The next part will be sketching a graph. But before we do the graph, just wanted to point out how the effect is cumulative. Right, so for first we found g of 0, then g of 1 was just one area, one figure to find the area of. G of 2, we took the first region and we added the area of the second region. G of 3, we were adding all 3. Now I wrote out all 3 separately. I wrote 1 plus 2 plus 1.3. But we could have just taken the result of the integral, the previous integral, which went from 0 to 2 being 3, and I could have just said it's 3 plus 1.3. And then for the next one, I could have taken the value for the integral 0 to 3, which is this, 4.3, and then put on the next term, which is minus 1.3. Right, so instead of writing all these out separately, I could have just said 4.3 from here, and then minus 1.3. Okay, so now let's move to the graph. We'll do that on the next slide, but I'm going to use all of these results because these are giving us ordered pairs. Right, when x is 0, y is 0 on the graph of G. When x is 1, y is 1. When x is 2, y is 3. And we go all the way down, we get a whole set of ordered pairs. We'll plot those and then connect them with a curve to create our estimate of the graph of G. I've copied here our results from the previous slide, and now we're asked to create a graph of G. So I start by making my x and y axes. Notice my x values go from 0 to 5, so I'll mark those off. And my y values go from 0 to 4.3. So let's go up to 5 on the y-axis. And then we just start plotting these points. So I've got the point 0, 0, 1, 1, 2, 3, 3, 4.3, 4, 3, and then 5, 1.7. And so you can see it's not a straight line. There's a little bit of a curve here, and then it changes directions and starts going down. So this is our graph of G. So what made it change from increasing to decreasing? If you remember the graph of F, it started out with being above the x-axis. And when we got to x-coordinate 3, the graph of F went down here to negative y values. And so remember, G is representing the areas always starting at 0 and going to some right endpoint. So let's say we picked the right endpoint to be 1, and then we moved to right endpoint 2, then to right endpoint 3. Every time we did that, the area got bigger because as we went farther to the right, you could see it got taller, right? We can't see the graph of F here, but we were making the region bigger by expanding the width. But then when we went past 3, F became negative. So we started incorporating areas that were being counted negatively towards the function G. So that caused the function G to start decreasing once we reached x value 3. Here we're asked to use area and area argument to find an expression for the integral we see here. So notice we're integrating the function f of t equals t, that's our integrand, and the interval is from 0 to x. So we're still dealing with this particular type of function where the right endpoint is the variable x. So let's sketch a picture of this graph. So y equals t, right? That's just the diagonal line that passes through the origin with slope 1. And then we can mark off the x interval from 0 to x, right? So the x is some unknown value. We'll just put it here. And that integral represents this area. So let's see if we can calculate that area. So it's just a triangle, so we'll use the formula 1/2 times base times height. The base is clearly x, right, because it goes from 0 to x. Now the height would be the y-coordinate of this point, and to find that y-coordinate, because it's on the curve f of t, to find that y-coordinate, just plug in the corresponding x value, which is down here, is x. So if you plug in x in place of t, the output would be x. So this point here is the point x comma x. And that tells us this distance is x and that distance is x. So now the base and the height are both x. So back to our area calculation. 1/2 times base, which is x, times height, which is also x. And so it simplifies to x squared over 2. Okay, so we were asked to find the integral from 0 to x of t dt. And we know that integral represents the area of the triangle that we sketched. And we just found an expression for that area to be x squared over 2. So we can see here, the result was a function of x. Right? The first types of definite integrals we saw where both limits of integration were both constants. The output was always just a number, and that number represented the area of the region corresponding to the integral. This time our output was not a constant number, right? It has x in it. And that's because we made the right endpoint variable. So the area depends on where you choose this x, right? If we choose x to be really big, you're going to have a much bigger area. So this tells you how to calculate the area for any given x that you choose to use. Now we're going to review the last two examples we did and look for an important conclusion we can draw. The example 2 that we just finished, we were given the function f of t equals t, and this was the integral we looked at, the integral of t dt from 0 to x, and we defined this as the function g of x. And then we used an area argument to find an expression for g of x to be x squared over 2. What I want to point out is if you take the derivative of this g of x formula that we found, right, you would just carry along the 2 in the denominator and take the derivative of the numerator, which is 2x using the power rule. That simplifies to x. So g prime of x is equal to x. But I also want to point out that's the same as f of x. Right? F of x means you plug in x in place of t, and so on the right you would have x. So it turned out that g prime is equal to f. And notice that g is a particular integral of f over where the right endpoint is this variable x. So by defining g as this particular integral of f, it turns out that g prime equals f itself. That's the definition of being an antiderivative of little f. So basically we're saying this particular definite integral where the right endpoint is a variable x, that this function here is an antiderivative of little f. Now we can draw a similar conclusion if we go back to example 1. In this example we were given a graph of f, not a formula but a graph. And we were able to figure out what the graph of this g of x, which has the same definition as in example 1. We defined g of x to be this integral, and we found some ordered pairs for g and plotted them and created this graph. So the question is, do we get the same result? Does it appear to be that this function g is an antiderivative of this function f over here? So to do that, let's start with g and see if we can figure out what the graph of its derivative would look like. So for that you need to look at tangent lines at various points and estimate the slopes of those tangent lines. So a good point to check might be like right here we've got a horizontal tangent, and that occurs at x value 3. So horizontal tangent means slope 0. So the graph of the derivative would have at x value 3, the y value would be 0. Well, notice over here we've got that. Similar thing happens at 5, right? Because it's leveling off there. There's a horizontal tangent. So at x coordinate 5, the y coordinate will be 0. If you look over here, there's the point 5, 0. Same thing here because it's leveling off at 0, a horizontal tangent. So at x coordinate 0, the slope is 0, meaning y coordinate 0. And you can keep doing the more detailed analysis, but basically if you were given this graph and you wanted to graph its derivative, you would get something similar to this. So that suggests that f is the derivative of g. Or another way of saying it, g is an antiderivative of f. So both of these examples are leading us to the same observation, that if we define g of x in this way, that will be an antiderivative of the function that's inside your integral. So it can be proven that the result we just saw is always true under certain hypotheses. So the basic statement that we saw in the examples we looked at is that if you define g of x to be this particular type of definite integral where the right endpoint is a variable, then this function is an antiderivative of little f. And another way to express that it's an antiderivative of f means when you take the derivative of that function, you get f. So there's some extra conditions here, right? That this theorem is only true if we assume f is continuous, right? And the result is that this function g will be continuous and differentiable, and that g prime equals f. So the idea that's really important here that we want to take away from this is that if you take a function f and you integrate it using this type of limit of integration, and then you differentiate, you get f back. This is what tells us the integral and the derivative are inverses of each other because they cancel each other out, right? You start with f, you integrate, you differentiate, you're back to f. Okay, so that's kind of what's summarized down here. So this is the important result of this theorem that's connecting differential calculus and integral calculus by saying that the differentiation and integration are inverses of each other. In this example, we're given this function g of x that you can see here and asked to find its derivative. So notice this g of x is one of the types of functions we've been considering where we have a fixed left endpoint and a variable for the right endpoint, and we're integrating some function. That's the kind of function we're considering in this fundamental theorem part 1. So first of all, let's identify the f of t here. That's the function being integrated, right? We call that the integrand. So it would be t over t squared plus 1. Before we apply the fundamental theorem to this problem, we need to make sure the hypotheses are met, and that is that the function f must be continuous. So let's look at this formula for f and see if we think it's continuous. So this is a rational function, and rational functions are known to be continuous everywhere on their domain. So what is the domain of this function here? It would only be undefined for values of t that make the denominator 0. And here that denominator is always 1 or bigger, right? Because t squared is positive. So the denominator there will never be 0. So that means the domain here is all real numbers. So this tells us f is continuous everywhere on all real numbers. So the fundamental theorem, the hypothesis is met. The integrand function is continuous on the whatever intervals we're considering. So here's the basic conclusion of the fundamental theorem part 1. It tells you that the derivative of a function defined in this way is the same as this inside function, but notice instead of f of t over here, it becomes f of x, and the x is whatever letter was used for the right endpoint. So here we're going to use this formula f of t, but instead of writing it f of t, we need to write it as f of x because of the x here. Okay, so g prime of x will equal f of x, which will be, using the formula, x over x squared plus 1. Okay, so we found g prime by using the fundamental theorem. Right? We didn't have to use any derivative rules or anything like that. It was just based on the fact that g of x had this form that applies to the fundamental theorem, and we were just able to use that result from this formula. We're given a similar type of function, but instead of calling it g of x, this one's g of w. And notice the right endpoint is also w. So that has to be the case for the kind of function we're talking about in this fundamental theorem part 1, is that the independent variable of g has to be the same as the right endpoint. And notice inside, when we wrote it before, we had f of t dt. Here we've just relabeled the t's with x's. So it's an f of x dx, right? Whatever the independent variable is here, the d whatever has to match that variable. So in this case, dx. And you want to make sure that the right endpoint uses a different variable name than the function and the dx, right? Now, in order to use the fundamental theorem here, you have to make sure this function is continuous. And tangent is not continuous everywhere. So we know there's an asymptote when this expression equals pi over 2, for example. But here we've limited w to go from, we could actually change that and limit it to go from 0 to pi. Right, because if w gets as large as pi, then the right endpoint is pi. When x gets to pi, this will be tangent of pi over 2. And tangent is continuous between 0 and pi over 2. So you have to put that restriction to guarantee that the function is continuous in this case. So here our f of x is tangent x over 2. And it guarantees that that function is continuous on the interval 0 to w. Okay, so now we can apply the fundamental theorem to find g prime of w. So because of the way g is defined, an integral where the right endpoint is the variable w, the derivative of this expression will just undo the integral, and we'll be left with this function, but it won't be f of x anymore. It will be f of the variable we used for the right endpoint. It will be f of w. And so now just look at your formula for f of x and replace all the x's with w. So we get tangent of w over 2. Okay, let's go to part B. Similar integral definition for g of x, but notice the right endpoint is x cubed, which is different from the x. So the fundamental theorem won't apply in this form. The variable here has to match exactly what the right endpoint is. So what we're going to have to do with this one is make a substitution. So we're going to just define the variable u to equal x cubed, because we'd like to replace x cubed with just a single letter. So if we do that, we now have the integral from 2 to u, and the rest can stay the same. And we want to take the derivative of this with respect to x. So the problem is there's no x's in here, right? But u is a function of x. So x is hidden in there. It actually is a function of x, this whole thing. We just can't see the x's. That is a chain rule problem. We're trying to take the derivative of a composite function because u has an inside part. Okay, so to find the derivative of this with respect to x, which is what we're asked to do, we first take the derivative with respect to u because u is the outside function. Okay, so then just copy the integral we just wrote. And then multiply by the derivative of the inside part. Right, so here again, u is a function of x. So the derivative of the inside part is just du dx. Okay, so we use the chain rule to get this. Now notice this expression here. We have an integral from a constant to a variable u of some function, and we're taking the derivative with respect to that same variable that's in the right endpoint. We can apply the fundamental theorem to this derivative. So this derivative will cancel out this integral and leave us with this function, but it will no longer be written in terms of z. It will be written in terms of this variable that's the right endpoint. Okay, so that derivative will be the square root of u squared plus 3u, and then we still have it multiplied by du dx at the end. We're not quite done because our answer needs to be in terms of x, right? We were given a g of x and we're asked to find g prime of x. So now it's just a matter of back substituting. So u is equal to x cubed, so we can replace these two u's with x cubed. And then du dx, we can find that by going back to this formula for u and just computing its derivative with respect to x. So let's do both of those things now. So we have the square root of, replace the u with x cubed. So we've got x cubed, which is then squared, plus 3 times x cubed. And then the du dx, if you look, u is equal to x cubed, so the derivative there is 3x squared. Okay. We could do a little simplification, for example. Here multiply the exponents, so we could write that as x to the 6th, but I think I'll just leave it at that for now. So we've seen some variations on using the fundamental theorem where we change the letter names around like we did here, changed the right endpoint, and here we changed it to x's instead of t's. Similar here, we changed the inside part to be in function of z, so it had to be dz to match. And then the other difference here, the right endpoint did not match exactly the x that was here, so we had to use a substitution to handle that situation. In part 1 of the fundamental theorem, this type of function here, this g of x that's defined as this special integral, played an important role in part 1 of the theorem. And that may seem like a strange type of function, right? We've probably never seen anything like this before. But it actually has many applications. These types of functions appear in physics, chemistry, and statistics fairly often. And here's one example, the Fresnel function, given by this integral from 0 to x of this particular sine function. So this is named after the person who developed this formula and who worked in optics. So it appeared in his work on the theory of diffraction of light waves, and it's been used even for later applications. One example is in the design of highways. So here's the Fresnel function we were just talking about. If you wanted to find the derivative of this function, if you didn't know the fundamental theorem, this would be a really difficult formula to deal with to try to find its derivative. But this is a very easy calculation using part 1 of the fundamental theorem, because notice the right endpoint is the variable x, and so we know when we take the derivative of this type of integral, the derivative will cancel out the integral and we'll get this inside function back. But we need to remember that we replace the variable of integration, which is t, with the variable here, which should also match the right endpoint. So we get sine of pi x squared over 2 for the derivative of that function. So over here we've had a computer graph two things. One is the s prime, which we've called f. I'm just going to label that. That's s prime of x. So that's what we're seeing in the blue curve. And then we've also graphed s of x in pink. So if we do some of our analysis from earlier of the relationship between the graph of a function and its derivative, you'll see that this fits it perfectly. So if you were given the graph of s without a formula, just a curve, and you were asked to graph the derivative, right, if you think back to those techniques, you would pick several points along the curve, sketch a tangent line, and estimate the slope at those points. And some important points to notice would be like where you have horizontal tangents. So right here, horizontal tangent, so at this x value, the derivative value will be 0, right, because the horizontal line has slope 0. And notice the blue curve has a y value of 0 at that same x coordinate. There's another one here, horizontal tangent, so slope 0. Notice the blue curve has slope 0. There's another one here, notice the 0. And here we also have a horizontal tangent right here at the origin, so that one on the pink curve, so the blue curve is also 0 there. And then you could pick other points, like right here. Tangent clearly has a positive slope, and notice it's positive. Right? So it's helpful to be able to confirm graphically that this formula we found for s prime does seem to match up with what the derivative of the graph of s should look like. Now I'm going to present part 2 of the fundamental theorem of calculus. And the proof of this part follows easily after the part 1 of the fundamental theorem, so I'll go over that after we look at this part. And the main use of part 2 is it provides us with a much simpler method for evaluating integrals, so we can avoid having to use the limit definition. So the idea is if you have a continuous function and you're trying to integrate that function over an interval a,b, you can evaluate that integral using this expression. Now the capital F here is any antiderivative of little f that you started with. So the idea is first, given this function little f, you find any antiderivative and call that function capital F. Then you evaluate capital F at the two endpoints a and b, and then you do the subtraction, f of b minus f of a, calculate the result, and that's the value of this integral. So I'm going to give you just an outline of the proof for why this works. So we're going to start by defining this function g of x that we used in part 1. So it was the integral from a to the right endpoint is the variable x of the function we started with, little f of t. So now I'm going to introduce the capital F, right? So just like it says in the theorem, let capital F be any antiderivative of little f. Well, one thing we know is that this little g is one antiderivative of little f. We learned that from part 1. Right? We learned that if you take the derivative of g, you get f. So that means little g is an antiderivative of little f. Right? So part 1 of the fundamental theorem FTC, fundamental theorem of calculus, tells us that g of x is one antiderivative of little f. Now, we just said capital F is an arbitrary antiderivative, so it could be little g, but it could be another antiderivative. So we learned not too long ago that to find the formula for all the antiderivatives, we call that the general antiderivative, all you do is you find one antiderivative and then you put plus c at the end. So that tells us that capital F, because it's an antiderivative, it has to equal this g of x plus some constant. Okay, so now that we've established this much, I want to look at this expression here. We're going to start with that and then simplify it to show that it actually equals this integral. Okay, so I'm going to start with capital F of b minus capital F of a. Now to find an expression for capital F of b, I'm going to use this formula. So it will equal g of b plus c. So that's capital F of b. Then we have minus capital F of a. So do the same thing. Use the formula for capital F over to the right. Plugging in a this time, we get g of a plus c. Now when you distribute this minus sign, you'll get a minus c here, which will cancel with that plus c. So that gives us g of b minus g of a. Now we can figure out g of a, right? If you look at this formula here, g of a would be the integral from a to a of our function, and when you have your two endpoints are the same, the integral value is always 0. That was a property we learned earlier. So we know that this g of a is going to be 0. So we end up with g of b. Now g of b we can rewrite using this definition of g of x. So if we plug b in for x, we get the integral from a to b of the function f. And this is actually what we wanted to prove. We started with this expression, and we kept rewriting it in equivalent forms until we got to this expression. And that's exactly what we were trying to prove. That's the statement of part 2 of the fundamental theorem. We're going to use the fundamental theorem part 2 to evaluate the two definite integrals in this example. So the first one, we see the function that we're integrating. We could notice it's in terms of x, so we could call it f of x equals x minus 1. We need to start by finding any antiderivative of this little f, and we'll call that capital F of x. Okay, so we've had practice with finding antiderivatives, so with a difference we can go term by term. So the first term is x. Using the power rule backwards, we get x squared divided by 2. Now we move to minus 1. The antiderivative of any constant is just that constant times your variable. So here it's minus 1 times x, which is just minus x. Now we could put plus c, or plus 8, or plus 12, right? Plus any constant, and that would still be an antiderivative. But it says any antiderivative. So the simplest one is to take the plus c just to be 0, and not even to write any plus any constant. Okay, so now we have one antiderivative. So now we're ready to go back to our integral. I'll just copy the integral we're asked to find. And the fundamental theorem says we take our antiderivative that we called capital F, we evaluate it at the right endpoint, which is 2, then we subtract, and then we take capital F and we evaluate it at the left endpoint, which is 1. Right, so the left endpoint came from here, the right endpoint from here, and you have to make sure to get them in the correct order, right? If we did f of 1 minus f of 2, we would get the wrong sign. So it's always f of the top number minus f of the bottom number. So now all that's left to do is evaluate these. So f of 2, we get 2 squared, which is 4 over 2, and then minus 2. Then we've got minus. Now we need f of 1, so that will be 1/2 minus 1. Now simplifying, notice in the first parentheses, this is 2 minus 2, so that's 0. And then here in the parentheses, 1/2 minus 1 is negative 1/2. Right? So we get 0 minus negative 1/2, which comes out to positive 1/2. And we're done. We've evaluated this integral. So just for fun, let's think about the area that we just found, right? Because we know definite integrals are finding areas. So I'm going to sketch the curve y equals x minus 1. So that's a straight line that has slope 1 and y-intercept negative 1. So let's see. For x, I only need to go out to 2, but maybe we'll go a little farther. Okay, so we just said the y-intercept is negative 1, and the slope is positive 1, so I could go right 1, up 1, right 1, up 1, right 1, up 1 to get some points on my line. Okay, so that is our function f of x equals x minus 1. Now we were integrating over the x interval from 1 to 2. So just this, the area below the curve would be this triangle. And this is an easy area to find. So for a triangle, the area is 1/2 base times height. So notice the base has a length of 1, and the height also 1. And we get 1/2, and that agrees with what we found using the other method. So this new method is very useful because most problems aren't going to be so simple where when you create the graph that it's very easy to find the area, right? Especially if it has a curved function instead of a straight line. That's going to make it so our geometry formulas are not going to tell us the area. So let's go to the second one. This time the function we're integrating is the square root of t, so we'll call it little f of t, which is the square root of t. We know we're going to need an antiderivative, so let's rewrite the square root as a 1/2 power. Now we want to find any antiderivative of little f, and we'll call it capital F, but now it's a function of t. So we use the power rule backwards. We increase the power by 1, so 1/2 plus 1 is 3/2. And then you divide by the new power, which is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So we could write this as 2/3 t to the 3/2. Now let's go back to our integral. Just copy it as it was given. Okay. And this equals, so I know it's going to be capital F of the right endpoint 4 minus capital F of the left endpoint 0. I want to go ahead and mention this notation. The way we typically write this when we're evaluating these types of integrals is you write your antiderivative, we'll just call it f of t, and then you put a vertical bar and you put your limits of integration, which are the same as what's on this integral here. Make sure they're in the same order, 0 on the bottom, 4 on the top. This notation means exactly what you see here. It says to take this function evaluated at this number on the top, then you subtract, and then you evaluate this function at the bottom number. Okay, so continuing on, let's find f of 4, capital F of 4. So that will be 2/3 times 4 to the 3/2. Then we subtract, and this time we plug in 0 into capital F. So that will be 2/3 times 0 to the 3/2. So 0 to any power is just 0, so this whole term just goes to 0. Now let's just simplify the expression here. So 4 to the 3/2, the 2 in the denominator here, like the 1, if it were 1/2, that would mean square root of 4. So we need to take the square root of 4, which is 2, and then the 3 means to cube the result. So 2 cubed would be 8. So we just determined 4 to the 3/2 power is 8. So we have 2/3 times 8, which simplifies to 16/3, and that's the value of this definite integral. So let's look at this one in terms of areas. If we were to sketch this function, f of t equals the square root of t, we know the basic shape of that curve is this. And the interval we're considering is 0 to 4. Okay, so the area that we're finding is this region. Right, and that's not something we could calculate using our geometric formulas because of the curved top. So whatever that region looks like, right, that's what the region looks like. We just determined its area is 16/3, which is a little bit bigger than 5, right? And so we were able to use part 2 of the fundamental theorem to find that area, which is the same as evaluating this definite integral. Now notice in both of these problems, we were able to evaluate these integrals without having to use the limit definition of the integral. And that is a really useful tool because, as we've discussed before, evaluating those limits in the definition of the integral is usually extremely challenging. We're evaluating some more definite integrals here. So in number 1, we've got the function we're integrating is 1 over x. So the first thing we need to do is find an antiderivative of 1 over x. So this is one that we learned. The antiderivative here is natural log absolute value of x. So then once we write our antiderivative function, we use our vertical bar notation and put the endpoints on it. And we know that notation tells us first plug in the top number, so natural log absolute value of 2. Then you subtract, plug in the bottom number, natural log absolute value of 1. The next, we can deal with the absolute values, right? So since 2 is positive, the absolute value of 2 is just 2. And then the absolute value of 1 is 1. And then we remember that natural log of 1 equals 0. And so it simplifies to just natural log of 2, and that's our answer. Okay, if we, just for fun, if we think of what area this is representing, we could sketch a graph of the function y equals 1 over x. So this one has asymptotes, right? We have one piece here and another piece here. So in green, that's 1 over x. The x interval we're looking at is from 1 to 2. And so here's the area that we just found. Okay, let's go to the second one. So here, the function we have is not written in a form where we can easily know what the antiderivative is. So we could rewrite 1 over x squared as x to the negative 2 power. So now, since it's written as a power function, we can find an antiderivative. Okay, so we can say this equals, use the, maybe we'll do it over here. So an antiderivative would be capital F of x equals, so you increase the power by 1, so the power goes to -1, and then divide by the new power. Usually we put plus c, right, but for these definite integrals we just need one antiderivative. We don't need to find others. So we usually just leave off the plus c. So this simplifies. We've got a negative sign from the denominator, and then x to the -1 can be written as 1 over x. So our antiderivative is -1 over x. We put our vertical bar with the endpoints. When we plug in 1, we get -1 over 1, which is -1. Then we subtract. Now we have to be really careful about negative signs. We haven't included this yet, right? The subtraction is always done. So plugging in -1 here, we get -1 over -1. Okay, so the first term is -1. Then we have in the parentheses, this is just +1. So then we've got a minus in front of 1. And we get -2. Now let's think about this one in terms of areas. The graph of this function, y equals 1 over x squared, we've got one piece that's here and another piece here. And we were asked to find the area from -1 to +1. And this one's kind of strange, right? Because it goes up infinitely high. But what doesn't make sense is we found a negative area. We got -2, right? So that does not agree with the graph. So what is the problem here? And it has to do with the function that we're integrating, which was 1 over x squared. Notice the vertical asymptote here at 0. And that is related to the fact that this is discontinuous at 0, right? It's undefined at x equals 0, which means it has to be discontinuous there. And the issue is the interval we're integrating over, -1 to 1, includes 0. Right? So it's discontinuous at x equals 0, and the interval includes 0. So this 0 is in the R interval from -1 to 1. One of the requirements for using the fundamental theorem is that the function that you're integrating is continuous. So we were not even allowed to use the fundamental theorem. So all the work we did up at the top, we weren't even allowed to do that. It's not going to work. So we say we can't use fundamental theorem of calculus. So at this point, we don't know what this integral will be. And I'm kind of running out of space to write this. Let me fit it here. So this is still, we get no conclusion. Now, having said that, you will learn a method in Calculus 2 to deal with this kind of situation. But for now, what we've learned is not going to tell us what this integral is. It's possible it doesn't exist, right? Because in terms of areas, it seems like this area could be infinite because it has infinite height. And it'll be an interesting result for you to see when you get to calculus that sometimes regions with infinite heights, as long as they're getting really, really narrow, fast enough as you go up, it's possible for that area to actually be finite. So that's something you can look forward to learning about in Calculus 2. But for now, we want to make sure that we start paying attention to this. You have to look at the function you're integrating and make sure it's continuous over the interval that's given here. Because if it's not, you can't do any of this. Right? So just to point out, this answer is incorrect. If you look at problem 1, this function is discontinuous at x equals 0. But notice 0 is not in the interval from 1 to 2, right? If you look at the graph, this interval from 1 to 2, the graph is perfectly continuous there. If this interval had been -1 to 2, then we would have had a problem. We could not have used the fundamental theorem like we did here. We're asked to find the area under the sine x function over the interval from 0 to pi. Let's make a sketch to see what the region is we're considering here. So sine has amplitude 1, and from 0 to pi is half of the complete period. Right, so the sine wave, right, comes up first, starts at the origin, it goes up first, and then does the negative part. So half of the period would just have that first arc that's in the positive region. Okay, so this is the function. It's just restricted to the interval that we were given, though. And so this is the area we're trying to find. So we know we can set up a definite integral that represents that area. So it's pretty simple to do. You just integrate over the given interval 0 to pi, and then the function that we're finding the area below is just sine x dx, right? So that part's very straightforward. Now we have the tools to evaluate this very easily. So we need an antiderivative of sine. Let's just come over here. So we would call that capital F of x. And so we've seen before, this is negative cosine x. That's the function that when you take its derivative, you get sine x. So I'm going to start using a faster way to get to the result without writing out as many steps as we did on the last example. So instead of writing f of pi minus f of 0, I'm just going to write our antiderivative, which is negative cosine x, and then put that vertical bar notation with the endpoints that were given in our integral. And then we learned what that vertical bar notation means. It says first you plug in the top number, then you subtract, and you plug in the bottom number. Okay, so I took this function, I plugged in pi, that gave me negative cosine pi. Then I subtract. Now I take this function, which includes the negative sign, and I plug 0 in for x. Now let's simplify this. So cosine of pi is -1, but notice there's a negative out in front of cosine pi. So we have negative, -1. Now the two negatives following combine to become plus, and cosine of 0 is 1. So we end up with 1 plus 1, which is 2. So the area that in this region that we sketched up here turns out to have area 2. We mentioned before how the fundamental theorem is important because it shows that the process of taking a derivative and the process of taking a definite integral are actually inverse processes of each other. So let's look at the fundamental theorem, both parts, and see how it tells us that. So here's part 1, and one way we could rewrite part 1 is here we have g prime, but g has this formula, so g prime means the derivative of this particular integral. So that's the g prime. And then equals will keep the right side the same, f of x. So in writing it this way, we can see if you start with little f, and you first integrate it from a to x, and then you take the derivative, you get f back. So in other words, the derivative canceled out the integral. It undid what the integral did. And the order here is you first integrate and then take the derivative. The derivative and integral undo each other. We get f back. Now let's look at part 2. In this case, remember capital F is an antiderivative of little f, which means little f is capital F prime. So one way we could rewrite this statement here is to replace this little f with capital F prime. And so now it looks like this. And we've also relabeled some letters, right? Instead of f of x with an x and dx, we changed it to a t with a dt. And then we changed the right endpoint to x. So over here, the right endpoint is now x. Everything else is still the same. So looking at this version, which means the same thing as the original part 2, here we're starting with a capital F, then we have a prime, so we're taking its derivative first, and then we're integrating. And you get capital F back, almost, right? It's capital F minus this thing here, which is a constant. So it's almost, except for that constant, the derivative and integral sign canceled each other out and gave us f back. Notice here the order though. First we're taking the derivative and then we're integrating. So whereas in part 1 it was the opposite order. First we integrated, then we took the derivative. So when you put the two parts together, it says no matter what order you do that in, if you compose a derivative with an integral, they undo each other in some sense. So they're inverses of each other. So I say in some sense because there are some technicalities, right? The integral here has to be a particular type where the right endpoint is your independent variable for your integral function, right? And in some sense down here, because you don't exactly get capital F back, you get capital F minus a constant back. So let's summarize what we did today. We finished up the very last part of section 5.2 on the definite integral. And here we looked at some of the comparison properties of the integrals. So which certain types of integrals that are less than or greater than the values of other integrals. And then we covered all of section 5.3, and this is the culmination of our work this semester, where we presented the fundamental theorem of calculus. And this is the theorem that relates the two major branches of calculus, differential and integral calculus. So the theorem has two parts. We first saw part 1, and this part involved taking the derivative of an integral. And it was a particular type of integral where the right endpoint is a variable. And then we looked at part 2, which was the reverse. It tells us how to take the integral of a derivative. Then we looked at some ways of using both parts. So one use of part 1 was if you're asked to find the derivative of one of these integral functions where the right endpoint is a variable. And then part 2 is going to be very useful as you move forward into calculus 2, where you're really getting into integral calculus, because part 2 gives you a very simple way in most cases to evaluate definite integrals without having to use the limit definition of the integral. So this completes our course for Calculus 1. We have got one more lecture left, and that will be a review for the final exam.